Let's talk today about quantum mechanics. You all know that the quantum mechanics is one of mechanics which is with us, even though it's not experimentally verified. You know that we do not have an experiment which is already verified, and we can say that the quantum mechanics is based on that postulate. Even though they are not verified, we have been using all these postulate for a quantum mechanics, which is very important topic for the century. You know that due to this we have many more devices and everything we have in our surrounding. We can see in this chapter, this is a chapter of a MSc class. You know, well, it is very easy chapter. If you listen all this thing, I'm going to describe all this term in the way you understand. All right, let's get started. Before starting this, you can see here introduction wave mechanics. We just know about what is wave mechanics, and in a second chapter, which is about quantum mechanical wave propagation. Third one you can see here is operator. Fourth one is here barrier penetration. Fifth one is harmonic oscillator and application, and the sixth one is quantum mechanical solution. You can see in the introductory part we are going to know about what the wave mechanics is, what are its inadequacies, that means some limitation it has, and how the Davidson and German experiment were were studied at that time, and how the de Broglie wave de, provided the de Broglie wavelength and a groove velocity, phase velocity, and uncertainty principle and its application. The Heisenberg uncertainty principle we will study in this introductory part. In the second one you can see here the equation of a wave propagation. The everything when shift from one place to another place, it may have path, it may have equation, means one of a locus which gives the path or way how it shift, how it propagate from one place to another place. We can see here two types of equation, which is very important to know the nature of the wave, that means position or time of the wave. You can see here, and Schrodinger means it is the name of a scientist who first studied the time dependent the wave waves, and and calculated one of a equation, and which we call the Schrodinger time equation. Well, the third one is time independent. That there are two types of a Schrodinger equation. One is time independent, another is time dependent. What they actually do is here they are going to know the specific position, that means coordinate, as well as the time where any wave is. We can know the information about the time and the position with the help of this Schrodinger equation. Alright, another one is normalization of a wave function, how they are normalized, what their expectation value of a dynamical quantity, and Ehrenfest theorem means expectation value. You can see there might be position, might be momentum, might be energy. We should uh, mm, explain all this thing in expectation value, the to provide whole information how to get the normalization of any wave function you may be dealing with, and you can also calculate the expectation value of any dynamical quantities means they are changing quantity, and with the help of Ehrenfest theorem we study in this. And next one is operator. The operator means at the time of a wave function traveling, we must have something to measure this wave function. All right, how to measure? If we have we have a any the suppose road, we have any length of a road, we have a length of a tree, we have a length of anything, we can use tape, the measuring tape. We can use this tape. In our school life we had used our scale, the to measure in centimeter, and we have a different measuring tapes as well to measure length. And here in a quantum mechanics we do not use all these, these quantities. We use just only operator are same like a tape, same like a, the measuring tape, or same like a scale we had been using when we were in our school. All right, operator means these are going with wave, the wave function, and there are remain unchanged but provide some values. We can say the eigenvector or eigenvalue provide. Whether they are commutating operator or non-commutating, means are they traveling together or not. Hermitian operator is also name of operator. We're dealing with a different kind of operator in this chapter. You can see orthogonal functional functions and orthogonality momentum operator. You can see that it can measure the momentum. Same the way you can get the different types of operator, the way you got this operator. All right, I'll be explaining a lot more about this. And angular momentum operator, box normalization, what are parity pair of equation of motion, and expansion of eigenfunction we study in this chapter. And barrier penetration, the some electron, some wave function wave travel from one, the wall to another wall, one wall, without the noticing whether it is present or not. For example, one wave is you have, and the just in between a wave there is a wall, and the wave is traveling, wave is penetrating this wall as if there is no wall. That means barrier penetration. We can know this tunneling effect. That is, if any waves travel without noticing, without the noticing about any wall, even if it is there, wall is there. That means tunneling effect, how the free particles travel, and what the condition of a particle in a box, how it come outside of a box, and a finite infinite potential barrier. We have a potential state or particle wave function as well. We can get a different reflection and transmission coefficient. It means how many waves are reaching, the crossing any wall, and how many are getting reflected back from there. We are going to study in this reflection and transmission coefficient chapter. And the last one, you can see, sorry, second last one is harmonic oscillator and application. From this one, what we know is here harmonic oscillator, here linear harmonic oscillator. Linear harmonic oscillator means the the your particles, so you are using some force in the particles in a wave, and due to your force, the particles is gonna change its position. The how the force is changing its position of any, the wave you have. We are going to study in its linear harmonic oscillator. Hermitian, the Hermite polynomials means one of a polynomials that describes the motion of a harmonic oscillator and oscillation wavelength, even an earth parity state. And energy of a harmonic oscillator, the how much energy is with, I have already told you that any wave travel from one place to another place, they may have momentum. And at the time of a momentum, having time in time, at that time, you can see, you can know there might be the energy with the harmonic oscillator, how much energy is with the any harmonic oscillator. We calculate this, and a 0 point energy and a rigid rotator at the time of rotating any rigid particles. What do you know the 0 point energy mean, and what the motion of rigid rotator? We will also discuss about this in the upcoming lecture. And last sixth one, you can see quantum mechanical solution, how we are getting the solution of Schrodinger equation for a spherical symmetrical potential. It means you have a spherical symmetrical potential. On this spherical symmetrical potential, how the wave function is traveling, how to get the solution of that wave function you can get from there. All right. And spherical harmonic, different types of harmonic motion, and their solution we're going to get on this chapter. And another is degeneracy. Third one is you can angular momentum, what the Legury polynomials, all these types of Hermite polynomials, Legury polynomials you might have studied in a bachelor, in the subject mathematical physics. Those who had studied, you may know about this. If you have not knowledge about this, I'll discuss more about this different types of polynomials and Legury polynomials. You can see Hermite polynomials, we have Legendre polynomials. We will discuss later on about all these one as well. And here solution of Schrodinger equation for a hydrogen atom. The how the Schrodinger solution of a Schrodinger equation for a hydrogen atom is, we study about this. And probable density of electron and shape of orbitals, how the density of electron and the shape of orbital is described. And transition probability and selection rule, that means while the electron jumping from one orbit to another orbit, how much energy there is, they're emitting or losing. We will study with the help of a probability and a selection rule as well. All this, of this quantum mechanics in this chapter of this mathematics, in this quantum mechanics chapter, what we are going to know about wave mechanics. What is wave mechanics? I introduced wave mechanics to you. And then wave propagation, the wave may not stay at one position, it may be traveling or one state to another state, one place to another state. What the quantum mechanical wave propagation is, how do we know? We have something, we use this. Then we use some operator, means like measuring equipment we've been using for our daily life measurement. We are using here operator as a measuring equipment for this quantum mechanical waves. You have a wave function. For this wave function you are using operator to get some eigenvalues. And here is barrier penetration. I have already told you, barrier penetration means how much penetration power any waves has. Actually you can, the particles have, and there to be come out of this any potential while potential state. Here we discuss everything I have already discussed in this. And here is introductory of wave mechanics. The scenario before 1900. Before this, in 1900, people did not know what the wave mechanics was. People were talking just only about classical mechanics that was only related to Newton first law, second law, and that would tell us that the mass would not change. Mass is a constant, and the energy, there wasn't any relation between mass and energy. What was the any the relation among them, due to which there is exchange of a thing, whether they are constant one, time dilution, different other topics weren't the studied or weren't described at the time before this 1900 AD. And after that, Galileo Galilei provided a law of inertia, which helped us to know the the how the inertia worked in our daily lives. And he described this law of inertia. later, after describing this, having talked about law of inertia, the Newton, the combined terrestrial earth and celestial space mechanics, you might have been wondering about, the earth and other terrestrial means those which are in earth, and celestial means which are in a space, how they have been, how all these bodies, whether that may be terrestrial or celestial, may have been, moving from one place to another place, or that means may have been getting the motion. And Newton combined this law, and the late earlier 19th century, the chronological order, everything, the what we are getting as a technology there, because of contribution, the many scientists, all they contributed a lot more about the science, the in a chronological order. You can see here Galileo hadn't, and this uh, uh, law of inertia been described by this Galileo, we would not have got this Newton combined terrestrial and celestial mechanics. Hadn't that been given at that time, we had not got, the vibration of atom and molecules. That means all the theory, whatever, all the theory or postulate, whatever were described at that period, they were interdependent on each other. They were interrelated to each other. The one had done some work now on which another step on, and wrote some new postulate and provided new, the discovery, provided new theory as well. In this way, you can see here, to talk about atoms vibration, molecules vibration, when then they're heated, Boltzmann and Clapeyron, the contributed to talk about them. That means to describe their phenomenon. At the time of heating, atoms and molecules were described by Boltzmann and Clapeyron. Same though, after that, electricity and magnetism and the light remained separated for a long time. All these topics were buzzword at that time, but they weren't as described as the way people could understand. They were remained separated for a long time. And by the end of the 19th century, the Maxwell, you can see the Faraday, combined electricity and magnetism and the light, and provided del B, the vector B is magnetic field, and equal to mu. You can see this mu into J, the current density. With this one, they combined, the electricity and magnetism and the light, all three in a one equation, and we got this in our quantum mechanics. You can see, let's we I should have talked about this when I started quantum mechanics. Why didn't I talk? Is here because, the quantum, to talk about quantum mechanics, we must know about this classical mechanics. The classical means the old science. The from this old science, people got some ideas, and they again put forward some hypothesis and proved and provided theory as well. And what were the classical mechanics? I'm gonna explain right now about this classical mechanics. The what the classical mechanics was at the time of the it was in its high position. The energy is directly proportional to the continuous spectrum, the 1980 Planck's law and black body radiation, E equal to NSF. The birthday of, we can take the 14th December Nobel Prize, plus particles. The discuss quantum means you might have been knowing this one packet of energy we call so quantum. And the quantum mechanics why failed, and as a result of this failing, of this classical mechanics, we got this quantum mechanics. And here are some, the drawbacks, some limitation, some, the weak point, inadequacies in the quantum mechanics. What were those? Here I'm going to describe. Here you can see the, the splines. After the spline and black body radiation, we got the uh, um, we got quantum mechanics. The what quantum mechanics really tells us is energy is directly proportional to the continuous spectrum energy, the which is which is taken as a body of this quantum mechanics as well. And here the classical mechanics could not explain the spectral line discrete. That means how the spectral line produced in any atom. That means electron when jump from one state to another state, whether the emitting any spectral lines or not. That weren't, that these all types of spectral lines weren't discussed about the discussed at the time of the quantum mechanics. And another one is variation of specific heat capacity. You can see here with the temperature and freedom of degree of freedom, cb equal to nk. The Dueling and Petit law were at that time. Einstein debate relationship there were, and their anomalous Zeeman effect. You can see effect is spine. It is one kinds of a Zeeman effect, which is related to spin. And another is stability of atom, fluid reactive effect. All these are very important topic in a quantum mechanics. They are discussed here in our mm, theory. We will discuss about them in the days to come. And inadequacies of the classical mechanics led to, the let to come the quantum mechanics. Here you can see you can see at the time of classical mechanics, here the people would say that the energy would be in the continuous energy spectrum forms. And but at the time of quantum mechanics, we could not say energy is in the form of a continuous energy spectrum. Rather, that means instead of that, we can say the discrete energy spectrum it releases. That means energy releases. We can say this right now. Well, literally, these are very important necessity of the quantum mechanics. You can see the classical mechanics is based on three Newton's law. You can see law of inertia, Galilean law, law of force, and law of action and reaction. And the quantum mechanics was based on um, Newton's three law. But now the this law includes the concept of absolute time, absolute scale, absolute mass. That means we cannot change the time, we cannot change the scale, we cannot change the mass, had been told to us. But later, the when experiment many experiments were done, what was revealed was all, the time, scale, and mass that changeable we got in the quantum mechanics. Okay, we're going to all describe all of them in the chapter next. All right. Three laws explain correctly motion of a celestial body like a planet, star, microscopic as well as microscopic terrestrial bodies moving with a non-relativistic motion. The non-relativistic motion at the time. Macroscopic means terrestrial. Macroscopic means they are large, heavy. Terrestrial means they are in a space. Sorry, they are in our floor of Earth. We can talk about them. The when they have non-relativistic speed. And we what the classical mechanics did was they just explained about the celestial bodies motion like a here planets and stars and terrestrial body. and that is v is very smaller than the c. If you have a v, it means velocity is very smaller than the light of velocity of light, then only we can explain about them. And where c is velocity of light. In inadequacy of the classical mechanics are as follows. Here I have written here some inadequacy you can see here, and there are also important. What are they? I'm going to explain here. All these inadequacies, what are the first one you can see here, it doesn't hold in the region of atomic dimension. That means it cannot explain the non-relativistic motion of atom, electron and proton and so on. That means the classical mechanics only explained about a heavy, the heavy celestial body, like a motion of a planet and motion of a star, motion of a heavenly body. But in case of atomic subpart, the subatomic particles, we cannot use this quantum mechanics, so that it would be the inadequacy of classical mechanics. In case of atoms, the electrons, protons, the neutrons, it cannot be used. That means classical mechanics cannot be used. Oh, it means it is failure to explain the motion of atoms, electrons and protons and so on. Another one is what it did not do, is what classical mechanics did not do, is here it could not explain the observed spectrum of a black body radiation. You might have studied it in a class 11. The if you are a student of a science, the black body radiation. And on that black body radiation, it that means it could not explain observed spectrum of black body radiation. The how much energy emit in the black body radiation, it wasn't explained at the time of quantum classical mechanics. And classical mechanics did not explain about this. You can get only all these, the spectrum of black body radiation in the quantum mechanics. Right, you might have been struggling with many problem, but do not feel the back. I'm here to help you, gear you up. All right, do not be back. Next, here you can see it explain the observed variation of the specific heat capacity of a solid with the temperature. How the specific heat capacity varies with the temperature, it cannot explain. That means classical mechanics cannot explain this, could not explain, so it failed. Another one is stability of atoms, how the atom remain all the time stable. That means about this it wasn't told anything in this one. Now had that been told, it could not be the inadequacy of the classical mechanics, but the stability of atom only is described here in a quantum mechanics. So the stability of atom, it would be the failure, that means inadequacy of this classical mechanics. You can see that it couldn't explain the origin of a discrete spectrum of atom. The what is the origin of how the origin of a discrete spectrum of atom, it could not explain. That means classical mechanics could not explain about this. Despite of these properties, the classical mechanics did not explain a large number of particles, like a photoelectron effect, Campton effect, Raman effect, and all these inadequacies which were in this classical mechanics led to the development of a quantum mechanics. Had the all these inadequacy been solved at the time when the classical mechanics was in its high position, we would not have got quantum mechanics. The due to this the weaknesses, due to this limitation, due to this inability of this due to this inability of quantum mechanics to describe all these things: stability of atom, origin of a discrete spectrum of atom, and a variation of a specific heat capacity with temperature, black body radiation spectrum, electron protons motion. We got new mechanics which explained all about them, all right, which we call quantum mechanics. And what was the black body radiation and the Planck's hypothesis? Here is described. You can see the spectrum of a black body could not explain could not be explained by the concept of classical mechanics due to its assumption that energy changes takes place continuously in 1980. You know, the if energy changes takes place continuously in 1900, you know, the people would know at the time of this quantum mechanics that the spectrum of black body radiation could not be explained quantum mechanics due to assumption. That what was the assumption was wrong because of energy changes takes place or took takes place continuously was told in a quantum mechanics, sorry, classical mechanics. But later when the Planck did experiment, he got that the every atom, you know, the every radiating atom in a solid emits energy in a discrete form, that wasn't in a continuous form. When oh, this fact was revealed by this flying, and whole the scenario was changed. You know, the energy of an individual one, you can see here the h as a Planck's constant, f is you know, the frequency of emitted radiation. And hypothesis was able to Planck was able to explain the law of distribution of energy in a black body radiation, how the energy distributed in a black body radiation. Who explained? You know, the Planck did, and explained this one. And this theory was given by the Planck in his historical paper entitled "The Theory of a Distribution of Energy in Normal Spectrum" as well. One of a paper which was historical paper where the theory of a law of distribution of energy in a normal spectrum was described, and which was given by the Planck in the 1900 December 14. This day is supposed to be supposed as a birthday of quantum mechanics. We can take after that day, you know, the having said that even and having said that everything, you know, the after this day what we got is quantum mechanics. We can take this date as a birthday of quantum mechanics. And here the Einstein extension of Planck's hypothesis, what was hypothesis which was given by Planck, was extended by this Einstein, and in 1905 they gave the remarkable explanation of all property of photo-ionic effect by applying Planck's idea of quantization to the light. You know, the Einstein uh, explained, you know, the extended the hypothesis which was given by the Planck, and in the way the people could understand with the help of a photoelectric effect, you know, the property of photoelectric effect. And what he used was the idea of quantization to the light, you know, the without hypothesis of without any contribution of the any, you know, the people who we another scientist could not do any, you know, the miracle invention, miracle, you know, the any theory. And what I really uh, uh, I'm going to say to you is here, oh, with the help of you know, the some other scientist, and with the help of their contribution, another scientist got a platform and did some experiment and proved. Here the same example you can see, Planck got the idea of quantization to the light which was extended by Einstein, and he did experiment in this photoelectric effect as well as assuming that, and he assumed as well a light is emitted or absorbed discretely, not a continuously, which was told in the time of classical mechanics. Later on in the 1907, Einstein successfully applied Planck's idea of quantization to solve the puzzling problem. You know, the people would have been knowing before this 19th century that the energy was in form of continuous, you know, the that is observed or emitted continuously, had been told in the time of classical mechanics. but after this Planck's idea, people knew that instead of a continuous emission or absorption of energy, we have discrete emission and absorption of energy, which is the new idea which is in the quantum mechanics. Quantum mechanics also uh, based on it. And the idea of quantization to solve problem in the 20th century, uh, in 20th century, regarding the observed variation of the specific heat capacity of a solid with temperature, the again, after this discrete energy, the energy form of a discrete emission or absorption of energy, what was given in the 20th century was the variation of specific heat capacity of a solid with the temperature. How the specific capacity gonna change with the temperature was observed, then which could not explain by the that wasn't explained by the classical mechanics before 19th century. The and applying the idea of quantization energy to atomic vibration, and Einstein deduced the formula of specific capacity of solid, which is experimental value was in agreement with the specific value. The agreement with experimental value, and describe the temperature dependence of the specific capacity of the solid. What was described at the before was deduced again by this Einstein. The which what is described was the atomic vibration in a crystal, and applying this idea, he explained specific capacity of solid, the how, and also calculated value of this of the solid specific capacity of solid, and what the value of experiment, what the value of a specific capacity of a solid was, in agreement with the experimental value, and described the temperature dependence, and specific capacity depend on the temperature, depends on the temperature was revealed later, and this assumption leads to the foundation of the theory of a specific heat capacity of a solid, and got this one. The and the same the way you can see that all these are the history, the what were done at that time, when the the in a chronological order, in the the date series, what had been done while this quantum mechanics developed. Everything you can see here, and before this one we described about uh, specific capacity, you described about discrete energy emission or absorption, we discussed about the specific capacities relation with temperature, with the help of idea of quantization, which was given by Planck. And after that, after described, after the uh, uh, 5 year, or sorry, 4 year, the after in 1911, Rutherford gave the planetary model of atom based on his absorption, and he described, and according to atom consists a small positively charged particle center consisting entire positively charged, and entire mass always concentrate at the center, and the entire mass, you can see the electrons circulate around the nucleus, who had been told by this Rutherford, but they could not explain the stability of atom and existence of the observed series of spectra. And in 1913, the Niels Bohr understood the common character of quantization of energy in blackbody radiation and photodielectric effect. And the specific theory of solid and a planetary model of atom gave fairly harmonious quantum mechanics, quantum theory of atoms. And he assumed that the radiation is emitted or absorbed only when electrons jump from one allowed orbit to the another allowed orbit. Before this assumption, people did not know how the energy absorbed or emitted or absorbed, hadn't been explained. After this Niels Bohr, what we got is energy emits or absorbs when it jump from one orbit to another. Before this assumption, and the electron can revolve in the circular orbit, which is angular momentum. And after this assumption, what was told is there the angular momentum must be the ns by 4 pi. The to be electron in any circular orbit. Without this angular momentum, and is by 2 by having any orbit can be in existence, electron may not travel in it, may not revolve in it. What has been told by this Bohr, and Bohr's theory is that based on the quantization of the circular momentum energy of electron in orbit. And the basic achievement of Bohr's theory that is rule out the direct link between a frequency or of a radiation emitted by atom and the frequency of rotation of electron in an atom. And what he ruled out means he got got a connection between a frequency of emitted the radiation by atom and the frequency of radiation rotation of electron in an atom. And here you can see that this implies that the frequency of light doesn't depend on the frequency of electron in an atom. And after the relation, Niels Bohr got what we can say after this relation of a Niels Bohr, the theory, we can say that the frequency of light doesn't depend on the frequency of electron in an atom. The Bohr's concept of stationary or discrete orbit experimentally varied by this one. The Bohr's concept of a stationary or discrete orbit was experimentally verified in 1911. That's all for today. What I talked today is about what the actually the contents in the quantum mechanics, and what the history of classical mechanics, and how the in the time series, how in a time series and the quantum mechanics developed. Here are some historical the points which I have described here. Thanks for your precious time, and tomorrow I'll have a next chapter which would be the video 2. In this way I'll be explaining in a way that it could be very easy to understand this quantum mechanics in the days to come. And don't be in a doubt. If you have any doubts and confusion, and do not forget to the comment in my channel, so as to mm, um, provide some the useful information. And I could be the explaining to crack your doubts in the days to come. I hope you'll subscribe my channel as well, and that would help me to the make some they create some useful video which would be related to quantum mechanics in the days to come. Thank you.